So in this video, I'm going to go over a classic ring closing mechanism. So in my previous video, I went over a ring opening mechanism, so I highly encourage you to check that out if you can. But yes, this is going to be a classic ring closing mechanism. Again, really high yield on free response organic chemistry exams. And even if you don't have free response exams, I still recommend you all to learn this because it's just classic acid-base chemistry, and it's going to help you. It goes a long way, so it's really going to help you understand acid-base chemistry much better. So let's go ahead and get started here. So I have these two alcohols here to my left as my starting material. Again, my catalyst is sulfuric acid. I like to write that as HOSO3H just because it's a lot easier to see. It's a lot easier than having to draw the Lewis structure, and that just takes, it takes a little bit of time. So I just like to write out H2SO4 as HOSO3H just because we know that's going to get protonated, or we know that hydrogen there is the most acidic hydrogen anyway, so it's just a lot easier to see that way. All right, so which alcohol here is going to get protonated first? So our first step is always protonation, right? We always protonate in an acid-base reaction, especially in this case, having a sulfuric acid react with an alcohol. So, but which alcohol is the one that gets protonated here? Is it going to be alcohol number 1, or is it alcohol number 2? So let's walk through this step by step and see why alcohol number 1 is the one that gets protonated. So if I protonate alcohol 2 first, so we're gonna have something like that. That's our little mechanism there. And if I protonate alcohol 2 first, I am going to get something like this as my intermediate, correct? So that's my hydronium ion right there. That's a plus sign. All right. So that is your intermediate. That eventually leaves forming this product here. Excuse me. Let me go ahead and erase this and make some space. Okay. So we get that. And we form a primary carbocation, right? It's our primary carbocation. However, we can have a hydride shift. If we do a hydride shift here, and shift one of these hydrogens over here, then we are going to get this lovely product over here, like so. And we're going to get a secondary carbocation. So this secondary carbocation is really favorable in this particular occasion, because not only is it a secondary carbocation, it's known as a benzyl carbocation. So it's also resonance stabilized by that benzene ring next door. So this carbocation can go into that benzene ring and can get resonance stabilized there. So that's a favorable situation, right? So having that secondary carbocation there. So let's go ahead and consider the alternative. Let's go ahead and work with this alcohol right there. So alcohol number 1 now. I'm going to go to the next slide and show you all. So let's go ahead and work with that, with this alcohol here now, right there. So if we protonate that one first, we're going to get that protonation. So we're going to get OH2 positive right there. That's our hydronium. And we don't do anything with that alcohol. We leave it as is. All right, and then that is going to leave, forming this product right here. Excuse me. So we form this product right here instead. So, you know, that's also a secondary carbocation. Excuse me, that is not a secondary carbocation. Sorry. That is a tertiary carbocation. So that's a tertiary carbocation. It's a tertiary. So in the previous example, we had a secondary carbocation, and in this example here we have a tertiary. And not only is it tertiary, but it's also resonance stabilized by that benzene ring. So not only do we have a better situation for our carbocation, so we have that additional resonance stabilization with the benzene ring. And because of that, because it's tertiary here, along with the additional benzene resonance stabilization, that is a better carbocation than this one right here, because this is, although this is secondary, and although this one also has that benzene resonance stabilization, this one is tertiary, so it's just a better situation. So that's why we work, that's why we're going to work with this alcohol here up top, because that's the one that gets protonated. That's the one that forms the most favorable intermediate, and in this case that intermediate is that carbocation. So let's go ahead and work with that, and we're going to go through. So let's go ahead and work with that. I'm going to change my background here really quickly, and let's go ahead and proceed with the mechanism. So the mechanism here is going to be something like this. Excuse me. All right. So first step is protonation. So we protonate, always protonate first. And you're going to form this product right here. So hydronium. Okay. Now, from there, you know, we have our good leaving group here. So the leaving group leaves. You're going to form water. So that leaving group leaves, forming water. And we form our tertiary carbocation there. Just like that. Okay. Now what happens here is this this oxygen with its lone pairs sees that carbon there is still, you know, even though it's still relatively stable because of the additional resonance stabilization through benzene, through this aromatic system here, and but it's still, I mean, carbon would still prefer to have 4 bonds, so, you know, that carbon there is still relatively electron deficient. So here we have an electron donating group, so the oxygen or the hydroxyl is going to act as a base, and we're going to have a Lewis acid Lewis base reaction here. So Lewis acid Lewis base reaction, so that oxygen attacks that electron deficient carbon, forming your, so that, and that's how you get that ring closure. So you all see that there? So you form a ring, and that is basically the ring closure. And essentially, excuse me, go ahead and let me go ahead and redraw that right there. So this is essentially what you form. So this is essentially what you make, and excuse me, I'm so sorry, I actually drew this. So the oxygen should be here. The oxygen should be there, and there's your bond. So why is that? Right, so this is the carbon we're attacking right here. We're attacking that carbon here. That's the carbon we're attacking. So that oxygen needs to be attached to that carbon right there. So that's the carbon here. That's the carbon that has those, that's attached to these 2 methyl groups here. So you have a CH3, you have a CH3, right? So just like that. So that oxygen is attacking that carbon there. So you need to attach that oxygen to that carbon with the 2 methyl groups on it. And so that's how we know that it's attached right there instead of how I drew it earlier. And so that's your intermediate basically. And so from there we can easily get to our final product, because in this step over here we formed hydrogen sulfate, so we formed HSO4 minus, and so that's simply going to deprotonate that hydrogen there, and that these electrons are going to jump on oxygen, and from there you're going to form your final product, which is going to look something like this. And of course you regenerate your catalyst, and so that's how you get the ring closer. So again, it's just a very, very, very common exam question for your response exams. You're either going to have that ring closer, or you're going to have the ring opening. Again, I'm sorry about this step right here. I accidentally misdrew that in this step right there. So just go ahead and pause the video and go back and make that correction. But thank you so very much for watching. This was a ring closer. Just stay tuned for more problems. I'm gonna be doing a little bit kind of the same difficulty. So just go ahead and stay tuned for that. Thank you so very much for watching.